The 2-minute video is probably a little too long. I'm going to show it anyway.
Well, we can, if you want, do you want to get it, is that your kickoff? Do you want to get it started when people start it now?
It's not a bad idea. I'll give it I'll wait until...
You start when, you tell
you tell me what you like.
You start when you should go first. When you should or not. You can just get going whenever you want.
Why don't I go 1 minute early,
right.
and then you can introduce me.
I'm absolutely fine.
I think that will, because if I start, it's 9:59 now, 8:59 now.
Right.
Have a picture.
Just go up, you have to be.
You can introduce me.
Good morning, everybody. Welcome to the last day of this workshop. It's been a great one so far, and we're continuing on this morning with all things Roman. And with that in mind, we have Julie McHenry here from NASA Goddard, the project scientist for the Nancy Grace Roman Space Telescope, who are giving us our first talk this morning. Thank you very much.
Thanks, Rebecca. Okay, so I showed the video of what we've got up to over the last 6 months or so. It's been really busy. Everything is coming together. What's shown here is a photograph of the Goddard clean room that I took on Monday. So what you can see in the front here is the outer barrel assembly. That's the bit that goes around the telescope. On the top is the deployable aperture cover, which is down, and behind it are mounted some engineering model solar panels. This is in preparation for thermal balance test imminently. Behind it is sort of the guts of the observatory. So you have the spacecraft, the instrument carrier that holds our 2 instruments, the coronagraph, which is a technology demonstration to demonstrate active wavefront control in space for sort of next generation coronography, and the main instrument, the wide field instrument, which is what we're mostly going to talk about here. That's the science instrument on Roman that is designed to give a large field of view, extremely stable observations. And on the top, of course, is the telescope. So this is a little clean tent, and it's what we're going to use to put around the equipment when we move it to other parts of the testing. What you're seeing here will be visible for, not very much longer, because we're about to begin a thermal vac test for OSD. We'll be doing EMI testing of SCIPA. These two components will have a parallel set of tests over the next few months. Then we'll put them together, some final tests, and send it down to the Cape and launch on a SpaceX. And we're on track for a launch in fall 2026. The actual date we're working to is October 31st, 2026, but I felt that screams were probably November. Although we actually have several months of margin to that date, so we're in pretty good shape. That said, to keep to this schedule, we're working really hard. The team are currently on a 2-shift, 7-day-a-week schedule. So those little guys in white are there from 7 a.m. to 10 p.m. Every day to maintain schedule. So that's it. I was going to show lots of other things with hardware, but I thought the movie and one picture probably captures all that you need to know. So the main takeaway is to sort of open with a punchline that Roman is really real. We're on track, and it's really time to prepare for the science. So if I have the kind of the sort of boring top level chart that what are the key things about Roman in a nutshell. We have a set of science and mission objectives. You could summarize them as do great astrophysics with wide field infrared surveys, address some of the grand challenge questions on the nature of dark matter and dark energy in cosmological studies, and to be more precise, to use measurements of weak lensing, a galaxy redshift survey, and supernova cosmology to have multiple different views of the expansion history and the growth of structure in the universe. We have an objective on exoplanet demographics, and to be more specific there, this is to conduct a survey using microlensing so we can fill in the relatively unexplored region from sort of the equivalent of the Earth radius out. And then finally, as I've mentioned, we have a coronagraph, and the purpose of that is to demonstrate active wavefront control in space. So for this mission, the cosmology and the exoplanet mission objectives drove the technical design. With the objectives that we had, we knew we were going to need a wide field view. We knew we were going to need efficient survey observations. We knew that we were going to need to be exceptionally stable and precise. And the requirements on stability is what allowed us to also be an appropriate platform for a coronagraph. But that is not to say that astrophysics isn't extremely important. And we're seeing that now because astrophysics is addressed in how we actually implement and execute the mission. This has resulted in the choice of when we had an option for an additional filter, what drove the choice of a K-short filter was astrophysics considerations. And right now, we're heading towards the end of our process to define our major surveys, and the much of the drive there is general astrophysics considerations. We're a survey mission, and as a survey mission, wide field of view, we're stiff. We can accelerate quickly, we can decelerate quickly, and we settle quickly. So we're very, very good at short exposure, move quickly, another short exposure, move quickly. Our power is in our ability to survey regions of the sky. We don't slew quickly, so we can't go quickly from here to here. We can just move efficiently on short slews. But because we're a survey mission, even one field of view with Roman, which is 0.8 by 0.4 degrees, you will have data that will allow you to address many different science investigations. So we have emphasized community cooperation and engagement to maximize our science return, because the way to get the best surveys isn't to have everyone in the community going to head in a proposal. It's to have everybody put their ideas on the table and then look at merging and consolidating them into an optimal set of observations. If you're surveying the sky 1,000 times faster than Hubble, you're going to have 1,000 times the data volume. Our data volume is a defining feature of the mission. You heard yesterday from Gisela on the Roman Research Nexus. We're also focusing throughout the mission on having lots of thought on consistent processing, on very good high-level data products. What we need to do is to operate in a way that minimizes, where possible, people redoing the same level of processing. I would say that that comes with an ask from us to you. Please work with us. Please engage with us. It is much more helpful to get input now on what we need in our pipelines than to hear it a year after launch, when our ability to make changes might be a little more constrained. Okay, so I think I've said some of this, but I want to, I haven't actually told you what Roman is, and maybe one of the later speakers will. I'm kind of sort of assuming you realize that we're a wide field of view observatory in the near infrared with slitless spectroscopy and a range of filters. We are in L2, which means that we do not experience Earth occultations. We don't go through the South Atlantic anomaly. So for a given amount of wall time, our observing efficiency is going to be roughly twice what you would get for observatory in a low Earth orbit. I've already mentioned our rapid slew and settle, and I really mean rapid, short slew and settle there. The same feature that allows us to have a very rapid settling time, which is a stiff observatory, also means that we helps give us a very stable point spread function. This observatory has been carefully designed to minimize jitter, to minimize disturbances. So we can characterize the point spread function and use that to get much better angular information. And then finally, we have an onboard flux calibration system because we have very precise calibration requirements. Okay, so it's not always, we have an observatory, it's what you do with it that counts. Roman has 3 large core community surveys. And these surveys are designed to address the science questions that were handed to us in the Astro 2010 Decadal Survey and confirmed in the Astro 2020 Decadal Survey. This set of observations makes up the majority, but not all, of Roman observing time. The galactic bulge time domain survey is looking at a few square degree region towards the galactic bulge on timescales of 12 to 15 minutes. Uses this to monitor over 200 million stars to discover exoplanets via microlensing. But those same data set will also enable the discovery of 100,000 exoplanets via the transit technique. It will enable the discovery of black holes via microlensing. It'll enable groundbreaking stellar studies by both looking at things like astroseismology and in stellar populations. So super exciting. This survey is almost certainly also going to include a field at the galactic center itself, which isn't optimal for exoplanet studies, but enables a huge amount of astrophysics. The high latitude time domain is a survey that you'll hear a lot more about from Brad. It's looking at tens of square degrees. every 5 days or so to find supernovae. It's driven by the need to address supernova cosmology, but it's going to have an incredibly rich science return. And I won't say any more about that because that's all Brad's job. And then finally, the High Latitude Wide Area Survey is several thousand square degrees of the sky in 3 tiers, deep, medium, and wide, to enable the measurement of the shape of over 100 million galaxies in multiple colors, to get spectroscopic redshifts of over 10 million galaxies, and everything else that you can do with that kind of data set. So I've discussed the surveys partially in the context of their exoplanet and cosmology objectives, but we do have an explicit requirement to conduct a large, ambitious survey to enable infrared astrophysics. And these surveys simultaneously address that requirement. In addition to that, we have somewhere between 15 and 20%, more than 20% time allocated to up to 30 additional surveys. These will mostly be selected via peer-reviewed proposals, but we may have some additional community-defined one. We have our first one already that I'll talk about later on the galactic plane. And that later is now. I'd forgotten that that was. We had a recommendation that perhaps we were leaving science on the floor by not thinking at all about any of the General Astrophysics Survey until very close to launch, because some surveys could really benefit from being defined early and having time for the community to plan. So we addressed this by soliciting input to invite the community to tell us, should we define an additional survey now? And if we should, what should it be? And the criteria were to really make the case that it was valuable to define it now. So this is defining the survey early, not necessarily executing it. We have the committee evaluated the white papers and recommended that, yes, we should proceed. The top-ranked theme was a galactic plane survey. So we have a committee that is working right now to define a galactic plane survey that will cover a large area of the galactic plane and very likely also have a time domain component. So this is exciting too. We define our surveys. This is really boring, but it's very hard for me to talk about what we're doing, where we are in the survey definition process without having a really boring chart. So the idea is that we have a committee for each survey. We have a lot of ways of collecting input. We ask for white papers. We have workshops. We solicit input as many ways as possible. Each of these 3 committees then processes the input that they got to arrive at 3 recommendations, a nominal, an underguide, and an overguide. And those wrote those up in reports that were released earlier this year. These were then handed to a top-level steering committee, the Roman Observations Time Allocation Committee, and there were members of that in this room. Thank you. Whose job it is to merge the various recommendations and pick between the nominal underguide or overguide for each of these surveys or something else. And once having done that, that will implicitly arrive at how much time is left for the General Astrophysics Survey pot. So we're almost at the end of this process. We anticipate being able to announce a result within the next month or so. So I want to, it feels, the process to define the community surveys has taught me a lot, and in some senses, surprised me. I think we massively broadened the science considerations for each survey. I think we also massively broadened the interest in the surveys and in Roman from the community. We got lots of really great ideas. People put lots of very careful thought. And the process of writing the white papers for this whole definition process also resulted in papers to the archive. So it just generated a lot more discussion and interest of Roman. And I think that had a little bit of a snowball effect and get more and more people involved. That was great. The new survey recommendations relative to the design reference mission that we had before all explicitly include recommendations that are targeted to astrophysics, which is exactly what we wanted. This was the moment that we really wanted astrophysics to also drive what we were doing. We meaning they, explicitly considered synergies with other facilities, which meant that we have more explicit thought in how to make sure that the Roman surveys are synergistic with Euclid and Rubin, and allowed Roman to really focus on its strength. So that was good. I want to change gear slightly and now talk about Roman's capability in the time domain, because it's not just how you use the observatory, it's also how you process the data. All Roman data is immediately publicly available. Our latency requirements are within 48 hours for the level 2 which is a calibrated single epoch image. This time is the time from the arrival of the data at the Science Operations Center, which is here. The latency through the rest of the system is very short. We have something like about 15 hours of downlink time per day, and we drain the solid state recorder each time, and the time to transmit data through the system is of the order 10 minutes. So that 48 hours is a requirement, which means that a large fraction of the time it's actually going to be significantly shorter than that, because we don't sit on the data and put it there after 48 hours. It's the whole system is automated and the data is available as it's produced. We have a rolling reprocessing scheme. So there's a requirement that reprocessed data are available within 6 months of kicking off the process. But we will be kicking off reprocessing on a survey by survey basis. So at any given time, there is likely to be some data being reprocessed. We have, and I've always had, a requirement to be able to accept target of opportunities. The way it's written at the moment is it's non-disruptive. That means that if a request comes in, we don't make a special command load for it. It just gets inserted in the regular planning and is uploaded in the next regular upload. That gives you a response within 2 weeks. How much within 2 weeks depends where we happen to be in the planning cycle. It is in principle possible to reduce this. As with many things, if you apply money, you get changes, but the within 2 weeks is the current requirement and is what you should plan to now. And then we were not actually explicitly designed for time domain astrophysics. And what I mean by that is that we didn't have any explicit requirements focusing on discovery space time domain astrophysics. I mean, obviously, our hardware capabilities and our actual survey plans are very capable for time domain astrophysics, because if you have to do exoplanet microlensing and supernova cosmology, you're necessarily going to be doing have observations that will enable time domain astrophysics. But what was missing was pipeline and processing infrastructure to fully realize that potential. And we addressed this by selecting a time domain astrophysics project infrastructure team who are developing a set of infrastructure that you'll hear about later in this session from Ashish. I'm going to move a little more briskly because I'm slightly running out of time. So Roman and external synergies, I mentioned the importance of other observatories. I really can't emphasize this enough. I think observations with other facilities are really going to act as a multiplier for Roman science, so we need to make sure that we don't make decisions that harm that. An obvious synergy is with the Vera Rubin Observatory. This provides, they will provide a deep, wide area survey in visible waveband, which would allow in principle to extend the Roman near IR into the visible, which is valuable for lots of reasons. We have better angular resolution, so can help Rubin with deblending. Rubin have also been a real pathfinder for community definition of surveys for flagship level observatories. And I think some of what I hope is our success with survey definition was inspired by the path Rubin took. We're currently working on identifying data sets of joint interest that are relevant early in the Roman mission. And the reason that we need to do that is that the Rubin data rights and Roman data rights aren't quite compatible. So to use Rubin data with Roman for most Roman science teams, we need to ask for a subset that have relaxed data rights, and we're working through that. For Subaru, we have a program with Subaru that the Roman Subaru Synergistic Program. There's 100 nights available as for use for Roman studies. We have a white paper call open right now that if you work really hard, you could get it in by tomorrow. But you're either you're probably already doing it or you're not planning to. We'll have a community workshop in later this summer to discuss the selected themes, and then we'll proceed with the detailed definition of the Subaru observations. And then finally, for Euclid, we've had really excellent technical discussions with the Euclid team because they're a pathfinder for using our kind of detectors in a wide field infrared observatory at L2. They're also Euclid is conducting observations of the galactic bulge region, which will produce excellent science for Euclid and really great precursor observations for Roman. So I had to get involved. I haven't left myself enough time to talk about the thing that I thought was really important, but fine. So we have a set of working groups, and these working groups are where the science teams, the science centers, and the project work together on things that the project need. So for example, the calibration group have been working on defining what are the calibration's touchstone fields going to be for the mission. This is the place where we're discussing the commissioning plan and looking for input. So one of the questions that we might want to address is, are we doing everything in commissioning that provides the information needed to enable all the ideas that people have for later general astrophysics surveys? We also, so there's a whole bunch of things here that I don't have enough time, but you should get involved. We also have recently kicked off a science collaboration, and these are separate. And they're separate because the work done in these groups flows into things that the project and the mission actually need, and the science collaboration is for general discussions. You can join the Roman working groups from this link if you're really quick, because I'm going to move on to, you can join the science collaboration here. We have proposal opportunities. You should ask me about it. They're happening every year from now. The deadline is in February, March timeframe each year. A few % of them will also include observations, and I'm phrasing it that way because your mindset really should be that primarily the Roman General Investigator Program is to get support to conduct Roman studies. I am going to just stop here, and we can then discuss this in questions.
Very much. We're going to take one question from online, because the rest of you in the audience can catch during the breaks and ask all the questions in all the other material here. So one more question.
The question online was, could you expand a little bit on the complementarity of between Roman and Euclid for cosmology?
A little bit. It's not quite my area. The Euclid survey is much shallower than Roman, but over a much larger area. So that gives a good cosmology figure of merit. Roman has a survey in the near IR compared to Euclid's visible, and goes significantly deeper and has multiple filters. So we have a very good handle on the control of systematics. It's very likely that combining the information from both Roman and Euclid will be complementary rather than competitive.
Thank you very much. With that, let's thank our speaker again.
I will, yes.
Okay. Now I'd like to introduce our next speaker. We have Brad Senko from NASA Goddard, who will give an overview of the Time Domain Astronomy program for Fermi. Thank you very much.
Thank you, Rebecca. Thank you, Julie, for that really nice overview of the Roman project. It's really exciting to see how far it has come and how close we are to such wonderful data and exciting science to be coming out soon. I'm going to talk about the broader time domain science, specifically from the High Latitude Time Domain Survey. I'm not going to talk a lot about Type 1a supernova and cosmology. That will come in the next talk, mostly with Ben. But just as a reminder, Julie gave us a nice overview of this. There are 3 primary core community surveys that Roman will be implementing. The Galactic Bulge Time Domain Survey, designed to detect microlensing exoplanets. The High Latitude Wide Area Survey, which is for baryon acoustic oscillations, galaxy space redshift distortions. And the High Latitude Time Domain Survey, which is designed to detect supernova at high redshifts, use those to constrain the cosmology of our universe. These 3 surveys have been put together what's called a design reference mission for those. That was done through hard work, many people working on over the course of a number of years, based off the requirements of the mission, and to demonstrate that the highest level science requirements, the level 1 requirements for the mission, could actually be achieved. Now, the great thing about a mission like Roman or any NASA mission is that we have wonderful engineers working on it, wonderful technicians, wonderful scientists. So when they actually build the hardware itself, it usually performs better than the requirements, right? That's what the requirements are, sort of the bare minimum of what we want it to do. And so what we have done over the course of the last year and a half is taken the new performance of the mission, and we have designed recommendations for the High Latitude Time Domain Survey that would allow us to achieve these great cosmology requirements from Type 1a supernova, but also to enable a much broader range of time domain and even more general astrophysics. And so this is what the charge to the High Latitude Time Domain Survey Definition Committee was. There are a number of folks who were involved in that effort in this room. If you are, could you just raise your hand so people can see? Excellent. You see many of them here. There are a few online. You all who are going to take advantage of the great data that the High Latitude Time Domain Survey is going to deliver should thank them. This was a lot of work. People didn't actually get paid for this, which is still somewhat of a source of both pride and confusion to me in our community. But really, a lot of hard work to make sure that there was, a great and sort of broadly optimal survey for the entire astrophysics community went into this. So please make sure you thank them. I think most of them accept beer if they don't actually accept our wine or whatever their favorite beverage of choice is while we're still here. Okay, so this is my only 1A cosmology slide in this talk. We have high-level requirements that the High Latitude Time Domain Survey has to meet, and of course we want it to meet. This is in particular to detect Type 1a supernova at much higher redshifts than we've seen from ground-based surveys in particular, and that Rubin will be able to detect. Because these sources are such nice standardizable candles, if you measure their light curves, you can infer a luminosity distance. If you then go out and measure a redshift, you can construct a Hubble diagram, constrain cosmology. This is to give you some sense of what we think Roman will be able to do when we combine the cosmological constraints from the weak lensing, from the baryon acoustic oscillations, from the type 1a supernova, to really pin down, what is the equation of state of dark energy? Do we really understand the sort of basic constituent products of our universe? But like I said, that's only a small portion of the science that can come out of a survey like this. We wanted to capture the breadth of the interest in time domain and even broader science that the community had. And so to do that, we got input from the community over the course of multiple years in a wide variety of formats: white papers, white paper pitches, white paper updates, community meetings, a working group that Ashish is going to tell you about. This is kind of a word cloud just showing you the types of things that people were interested in doing with the high latitude time domain survey. Again, you can see everything: cosmology, galaxies, supernova, supermassive black holes, broad range of astrophysics. And so when we were sitting there thinking about how we wanted to structure this survey, we really tried to focus on what makes Roman unique. What are the things that only Roman with a high latitude time domain survey can do that we're not going to get from Rubin, that we're not going to get from Euclid, that we're not going to get from other ground-based and space-based facilities. These are not profound thoughts, but of course the near-infrared allows us to push to high redshift, allows us to study things that are dusty and cold. The fantastic angular resolution allows us to study things in complex environments, the nuclei of galaxies, for example, that we can't necessarily do from the ground where the atmosphere gets in the way. Low resolution spectroscopy, this is really, something that's kind of a first over, really wide areas, right? It's a very unique capability, and we thought long and hard about how best to take advantage of it. And high precision. Julie mentioned this, but this is something that I think people don't think a ton about. But Roman is really going to be an order of magnitude better in terms of the photometric precision that it's going to achieve, and how can we capitalize on that to enable a broad range of science. And then the other thing, what makes Roman unique? What does the broader landscape look like? Rubin, Advanced LIGO, Virgo, IceCube, all these other facilities. How do we make sure we design a survey that can take advantage of all of those? What we realized very quickly was that unlike type 1a supernova, there was no single science case that clearly stood above the rest. The great thing about type 1a supernova, in a sense, you can kind of distill it down to a single number, this dark energy task force figure of merit. Of course, that's not all the science with type 1a supernova, right? But that's a nice, simple metric. And so we tried to enable a broad range of science. And, not surprisingly, right, a survey that's designed for type 1a supernova is compatible with most of the other transient science that people are interested in, right? If you think about the ground-based optical surveys like ZTF, like ATLAS, like Pan-STARRS, Assassin, all these things are finding type 1a supernova and all the other range of transients and explosive sources and variables that all of you are interested in. And so, for the most part, the things that people are interested in were quite compatible with the, kind of type 1a and the design reference mission. There were a few things that, we flagged that were probably not, and we'll come back to how to enable these. Target of opportunity observations, obviously. Really high cadence, in particular because the type 1a supernova are looking for things at high redshift, and they evolve over time scales in their rest frames that's of order of weeks. You really don't benefit in any way from looking at them at like a daily cadence or something like that. And that eats up into area that you could be using on your survey. And nearby galaxies, galaxy clusters, you can imagine for low luminosity things, dusty things. It's just not, not what you're going to do if you're looking for things that are at higher redshifts. Okay. Just a few of the science cases we've heard of these that, were in the back of our minds as some of the really compelling and exciting things we wanted to make sure we enabled. Gravitationally lensed supernova, there was a whole talk on this. Lensing from a massive galaxy or cluster in the foreground can give us nice multiple images. Here's supernova ref stall. The time delays, we can use them if we know the potential, gravitational potential in the lensing galaxy to constrain cosmological parameters. There's something like 6. I think the talk earlier showed maybe 9 of these are known. Roman could do, orders of magnitude better than this. This is a great, independent way of doing cosmology, and also these images are just, really cool. Apparent stability from the early universe. We heard, talking a lot in the sort of breakout session about the earliest population 3 stars, low metallicity, distinctive terminal explosions. Apparent stability, this is when the process, when pair production reduces the internal pressure, ultimately leading to a runaway explosion in the core of these very massive low metallicity stars. Because of their large progenitor mass and radius, these things are going to give you sources that are very luminous and very long time scales. Okay, so this is something that we were definitely thinking about. If you have a transient that's lasting multiple years, how do we enable that in the survey that we're designing? And of course, because these are at high redshift, you're going to get very red colors. This is just kind of showing you the phase space here of where type 1a supernova fit in, like a color magnitude diagram here for a couple of infrared Roman bands. 1a supernova, core collapse supernova, superluminous supernova, and the parent stability supernova, kind of poking out here on the very red end of this phase space. Our process, kilonova, neutron-rich ejecta from binary neutron-star black hole mergers. You're getting these very heavy elements, lanthanides, actinides synthesized. You get a very high opacity due to Leiden blanketing from the many transitions in these heavy elements. This naturally leads you to something that's quite red, that Roman, with its sensitivity and field of view, should be quite good for. You can imagine discovering these through a bunch of different channels. The obvious one is following up gravitational wave triggers, and there will be sensitive gravitational wave detectors operating when Roman is up there. You could imagine doing them from short GRBs or even from blind surveys. That's something that we'll talk about a little bit more as we go along. And last, tidal disruption events. You have star torn apart by tidal forces. The returning debris results in a long-lived. Again, this is sort of, very long time scales. This is something that we were thinking a lot about. Allows us to study black holes and quiescent galaxies, the physics of accretion. And Roman is really nice for these. Intrinsically, these sources are very blue. And so when you think about going out to high redshift, you actually benefit from this, strong positive K correction that allows you to detect them out into, much higher redshifts than ground-based facilities that you might just naively expect when you're thinking about higher redshift sources. Okay. So how did we synthesize that all into a series of recommendations? I'm going to just summarize this in a couple of slides, and then please remember that these are just the findings or recommendations that we made, and the ultimate decision for all of this is going to be decided by the ROTAC, the Observatory Time Allocation Committee, that's trying to synthesize all of these disparate recommendations into one coherent program. The main survey is going to be conducted in the sort of central 2 years of the 5-year Roman mission lifetime. This is re-imaging a couple of different fields every 5 days for this entire 2-year period, to give you these really nice light curves, multiple bands across a couple of different areas that will be the primary discovery machine for the type 1a supernova and all the other transients that we're interested in. But as I said multiple times, there are lots of things that are evolving on really long time scales, in particular high redshift sources, rare sources that we were quite excited about. So we wanted to make sure that we had an extended component with a lower cadence that will allow us to have some sensitivity to these sources. And we also wanted to make sure that we had a survey at the beginning. You can imagine if you're actually waiting, a year and a half to conduct your first observations, there's some risk associated with that. What if we find that our survey design was, not optimal for some reason? What if we find that the rate of type 1a supernova at redshift 1.5 is not what we thought it was going to be? And so we wanted to have the capability to build up reference imaging of our fields and to really test out all our pipelines, all our assumptions. And so we have recommending a small pilot survey at the beginning that will allow the community to engage early and make sure that all our recommendations are really, sort of optimal when the bulk of the time is kicking in here. In some detail, what that looks like, this core component was, sort of designed in terms of depth and filter coverage with 2 tiers, a wide tier for imaging and a deep tier. And the wide tier was designed in terms of filters and sensitivity to detect type 1a supernova at a redshift of about 0.9. So to pick up, right kind of where Rubin is dropping off. And the deep tier was designed to detect type 1a supernova out at redshift 1.6, I think, or 1.5 was kind of the median distance. And so if you look at where Rubin is going to be finding things, typically in the deep drilling fields, it's going to be at redshift 0.5, 0.6. Then the idea that Roman picks up and carries us from redshift 0.5, 0.6 out to about redshift 2 to give us this nice long lever arm on the type 1a supernova. We also wanted to make sure that we had, a sizable fraction of time spent on the prism. This will allow us to take spectroscopy, to do classification, to do characterization, to do science that, again, is really unique to Roman and not possible with any other thing. At the same time, the prism observations are really expensive, and we wanted to make sure that we were getting, the bulk of the time in imaging. The idea for cadence, or to say this, 10-day interlaced cadence, so actually revisiting the fields every 5 days. So for the wide field, on day 1, go in R, Z, and J, and day 5, go in R, Y, and H, and then cycle back on, day 10, R, Z, J, day 15, R, Y, H, sort of, so you're visiting every 5 days, but you're getting the full filter set every 10 days. Slightly redder bands for the higher redshift, deeper tier, and a 5-day cadence for the prism. For the pilot, it's really just the sort of same survey design here, but with a slightly different cadence for these observations. 8 visits to make sure we're getting all the fields in the first 5 months. And then the extended component, long-term monitoring. This is just of the deep imaging fields to give us the really high redshift exotic transients spaced out over the full 5 years. Where the fields are located, we thought there would be tremendous benefit to splitting these up into both another northern and a southern tier. And the southern tier, we recommended the Euclid Deep Field South. These need to be in the continuous viewing zones. For Roman, that really limits somewhat some of these, very popular survey fields like the Chandra Deep Field South or the Cosmos field, which are more equatorial. But the Euclid Deep Field South we thought would be wonderful because of synergies with Euclid, because this is one of the new Rubin deep drilling fields. And we're hoping that this will motivate people to go out and get really great extensive multi-wavelength data to characterize it before Roman actually flies. And in the north, the Elias North 1 field is where we're looking, and this is what just the wide and deep tiers would look like sitting in that. Okay, so those are our recommendations. Again, please keep in the back of your mind that all of that is contingent on the ROTAC, over the course of the next few months, synthesizing all of these things and making sure that it does make sense, and you can execute all of the different survey recommendations together. I wanted to spend the last couple minutes of my talk thinking about how we prepare for all of this great stuff that's coming, and a few thoughts in my mind. Number one, we have tons of experience with optical transient surveys. We have less with what's going on in the near infrared. We heard some interesting things about NEO-WISE. There are new facilities on the ground that are that are either just recently coming online or have recently come online. I think there's a strong impetus for us to take advantage of these to calculate rates, to develop classification tools, and really familiarize ourselves with the range of things that we're going to be finding at these wavelengths, because they're not exactly the types of things that we're going to be finding at optical wavelengths. Complementary data sets, Julie mentioned this. There are 100 nights of Subaru time reserved for joint Roman Subaru science. For the high latitude time domain survey, this could be host galaxy spectroscopy. This could be concurrent transient classification, characterization, concurrent imaging, either spectroscopy, with the prime focus spectrograph, or optical imaging with hypersuprime cam. I think there's a great need, because of the fields that we selected, for other multi-wavelength data sets, particularly for people who are interested in things like AGN, X-ray characterization, radio characterization. So I hope that if and when these fields are confirmed through the ROTAC process, that we as the transient community work with the Galaxy folks to start to characterize those fields even better than they are now. And the last thing, which Julie was sort of getting at the very end of her talk, was complementary programs, the science that's not going to be necessarily enabled by the high latitude time domain survey. One obvious thing is target of opportunity observations. There's going to be a very limited availability of TOO time through the guest observer program. I think Julie mentioned that she was expecting something like 30 guest observer programs in total to be recommended in cycle 1. You can imagine that TOO observations are going to be a relatively small fraction of that. And so the project is thinking about this, trying to strategize for what are the most impactful, what are the most compelling ones, and is planning to organize a community workshop to allow people to brainstorm, to think, if they're interested, to work together, to coordinate, to put together target of opportunity proposals. If they're not interested, even just to share ideas would probably be useful. I think it's also really good for us to start thinking about what other science is being missed by the high latitude time domain survey. I mentioned higher cadence observations, which really can do the daily science, the daily cadence for this. The other thing that seems obvious to me, nearby galaxies and nearby galaxy clusters. This seems like a really natural way, in the same way that the high redshift folks with JADE and JWST sort of collaborated with the people doing the galaxy science and doing this in a cadenced way. This seems like a really good opportunity for us in the time domain community to collaborate with people who are going to be studying and getting these really nice observations of nearby galaxies and galaxy clusters. So I think that's it. I'll finish right here. Thank you all very much. Happy to take any questions. This says low battery on it. I don't know where it's supposed to go. Okay.
Any questions? So we have one at the back there.
Brad, I think Julie mentioned a 5-year mission. Is that nominal, or might it extend much longer like we anticipate for JWST?
I'll let Julie answer that one.
It's similar to JWST. It's the 5-year requirement, 10-year goal, a much longer aspiration.
Okay, so it's not like you run out of any critical fuel to nudge it back into place or anything like that?
I mean, our consumable is propulsion fuel, but I mean, there will be lots of margin on that, and we're built to be refuelable. So if at some point servicing happens at L2, we could actually be refilled.
Brad, what's the plan for kilonova science on the 2-week TOO timescale? I mean, obviously, that's not going to allow other wavelengths to happen in parallel.
Yeah, it's 2 weeks is on the long end, but you can imagine, right? There's scenarios where Rubin looks, doesn't see anything, maybe because this is a black hole neutron star source and it's very red, or whatever reason, there was none of this blue kilonova that was associated with it. There could well be, I can imagine scenarios where, okay, we didn't see anything in the optical, but we want to go and chase, of order 10 square degrees in the near infrared, and 2 weeks is not a crazy time scale to do that. I mean, it's a little long. It'd be nicer to be, of order 1 week, but that's kind of the thing that I had in, but if, we should have discussions about this, definitely.
So I was wondering about the field selection for the wide and deep. So it looks like for the north field, the deep is appeared inside the wide one, whereas it's different for the south one. What was the consideration that led to this design?
Yeah, so the way that Rubin is doing the Euclid deep field south, and this is, someone from Rubin should correct me if I'm wrong from this, that maybe is in the audience. They're still discussing this, but they're planning on doing it 2 pointings, where there's a little bit of overlap between some of them, and with a slightly different, not exactly a daily cadence. So I think we were trying to take advantage of the way that they were doing this and getting our deep field where they were going a little bit deeper, and getting our wide area where they were going a little shallower. If someone from Rubin wants to correct that, please.
Yeah, it's just, that Euclid area is 2 Rubin pointings. And so to get the full, so it was chosen previously, that it would basically Rubin would go to half deep drilling field depth on those 2 pointings, and so it's gonna try and dither kind of in between, so to cover that region. So.
Yeah.
Okay. Does the Roman CVZ overlap with JWST CVZ?
I don't know. The Roman CVZ is ecliptic coordinates above or below 54 degrees. I would assume it would be similar for JWST, but I honestly don't know the answer to that.
Yes, so you mentioned something we're missing perhaps is high cadence. So would you, or would the committee consider rolling cadence consideration, something similar that LSST?
So we thought about this, and it seemed like we thought for the core, component, that doing it with the fixed cadence, we're going to get a rolling cadence to some extent, because it's not going to be possible to schedule every 5 days exactly. And so, we're going to get 3 days, we're going to get 7 or 8 days. It's going to be mixed in a little there by default. But our thought was, if you really wanted higher cadence than that, it's just hard to justify, and it's really incompatible with the type 1A science.
Nobody said what the angular resolution is. What is the resolution at 1 micron?
I'll leave that for Julie or someone here.
People said it was remarkable, wonderful, unprecedented. But what is it? Is it diffraction limit? Will you be at the diffraction limit for the?
I think you mean imaging.
But for the imaging.
Yeah,
It's HST like. It's still understandable.
It's undersafe. Well.
Let's give him the next talk, hence we defined.
8 more pixels. Okay.
Yeah.
Questions? If not, let's please thank our speaker.
Sorry, I'm stuck here.
And now introduce our next speaker, Ben Rose from Baylor University, who's talking about supernova cosmology with Roman.
Thank you. I assume the mic is working right? Online too? Well, you'll let me know if it isn't. So we have started very wide with Roman, and now we're getting to a very specific topic. And so I hope to not put you all to sleep, because I know this room is full of cosmologists. But I do have a different picture of Roman. And so you can see this was taken about 6 weeks ago with wide field instrument here. It's on there. They can't change it. Well, they could if a disaster happened, but no disasters. So I'm just waiting and excited to see it launch. You didn't say this, Julie. Launching next year. And we'll see what the engineers have been able to do and build, and I'm excited. So as a cosmologist, I like to just generally ask the question, how is our standard cosmological model working? How is Lambda CDM doing today? Well, probably not as well as it has been. So there's two sort of things right now. If you measure the early universe, the CMB, and then you take this Lambda CDM model and you propagate it to today, and you make a prediction of what the expansion rate should be, you get an expansion rate of 67.7 kilometers per second per megaparsec. Then if you go out and measure it, one of the most precise measurements today is getting around 73 kilometers per second per megaparsec. And they're disagreeing at about 5 sigma. There's some questions with other tests about what's happening here. Is this is this actually seeing something about the universe and physics, or are we seeing just systematics in one or both of these measurements? But how's Lambda CDM doing? Well, it's unsure about the current expansion rate. Also, it's unsure about if it's a cosmological constant, if it's lambda. So this is the DESI results that came out recently. I hear there's updates coming soon. And so if you look at the DESI and the DES collaboration, I was part of DES, and so that's the one I really like, the green one here. You see that lambda CDM, this upper corner piece here where the two lines cross, is ruled out at about 3 sigma. So it seems like in the most recent supernova and most recent BAO measurements, when you combine those two, you seem to find a dynamic dark energy and not something that's just static. So how's lambda CDM doing? I'm not sure, but what I am sure about is Roman will help us understand and answer this. I have to start with this. So Brad was talking about all of the different transients we were going to see, and there's been a recent simulation about these transients, and NASA just this week added sonification to it. So we're going to see and listen to this, where the volume is the brightness and the pitch is the color. Still going. There's going to be a lot of transients there. So for all you non-cosmologists, most of them aren't going to be 1As. There's going to be a lot of interesting things happening there. Brad has talked a lot about that. But let's go into the 1A cosmology goals. So Roman is going to be a, quote, stage 4 cosmology mission. That means it has a goal of measuring the equation of states of dark energy to a certain precision, which ultimately means that there's about a deviation from lambda CDM of about 6 millimags. That's where we get our photometric precision requirements for Roman. So the supernova cosmology is driving millimag precision photometry, which every other science case just gets, which is exciting. But what's exciting also is that the DESI and DES results are seeing actually fairly substantial changes from lambda CDM. Significantly larger than a 6 millimag deviation. So if this result is to stand, and that is actually what the universe is those exact numbers, Roman will have excellent precision on measuring those. And we'll really be able to distinguish that from lambda CDM, which makes me excited. But I like to not just talk about it in abstract, but actually look at the data set itself. So we've seen some Hubble diagrams before. And the original Nobel Prize was with, what was it, Bob? Was it 30? Yeah, 50. High Z was with 50 objects. The low Z and high Z was with 50 objects. DES has 1,000, about 1,200 objects at a higher redshift. Roman's going to observe over 15,000 type 1A supernovae. And our peak is going to be above redshift 1. Most of these objects are above redshift 1, whereas today we have about a dozen or 2 dozen objects above redshift 1. We're going to take that and bring it up to nearly 10,000. And Brad, you mentioned that it was going out to about redshift 2. I want to point out that we're going to get about as many as we have now above redshift 2. So we're on the order of 1,000 1As in our cosmological samples, and we're going to get less than what we have today, but about the same order above redshift 2. It really is an unprecedented size and like location in the universe, age of the universe. So that really brings us, oh, I wanted to show this too, sorry. So these are simulations of the light curves from the wide tier. So you can see that lower redshift, here about redshift 0.4, we get an excellent near-infrared light curve. If you go about to redshift 1, it gets a little rattier, but it's still pretty good. The wide tier, which was targeted at redshift 0.9, is still able to see at about redshift 1.3. And for all of you UV people who love the rest frame UV, can I have some data? Because my model gave out. There's no R band here, not because we won't see it necessarily, but because I don't have enough information in the UV. So just in the Y tier, we're going to get excellent information from the rest frame near IR all the way out to the UV. Okay, where am I going? Oh yeah, the time series. We do have Prism, and so the Prism is interesting. It's not like what you're used to. Because of its expense, because it's slitless, there's a lot of background on it, and so it's really hard to get a single exquisite high resolution, like high signal to noise spectra. But because of the multiplexing, you can come back day after day after day, and so we're going to get the information in time that you wouldn't necessarily get before. And so here's 2 example time series. I've actually want to put the call out here. All of our typing is really based off of a single spectra. If anyone knows of typing a time series where you can input all of these, please let me know because we need it. If anyone wants to work on that, also please let me know because we need it, because we're gonna not just have spectra at max, like here and here, but we'll have the whole time series that we need to gain the signal to noise from all of that information. I just realized my clock is hidden. I found it. I'm good. Okay. So the data is unprecedented, and it's at a completely different redshifts. And this worries us cosmologists a little bit. Some of the JWST observations are sort of trying to test some of these concerns. But I just want to point out again, so here is the DES data set, including the low Z sample. And here's what Roman's data set might look like. And here's the whole phase space that is 100% new. And with 1A time delays from star formation to explosion, the peak of cosmic star formation affects 1As at about redshift 1. So that means we are influenced by a decaying star formation rate above redshift 1. So you're at that rise of cosmic star formation rate. So you're very young stars, you're lower metallicity than you're ever used to. And so that, in a very different types of galaxies. And so we have looked at these systematics, host galaxy corrections, what's the standardization, the scatter around the standardization, how is the dust affecting these? I guess more host galaxy, measuring. Are we able to actually measure the host galaxy properties right? And there's so many more. We have looked over the last 15 years and beyond at all these different systematics. And they're all going to change and be worse and be different. And so that really is one of our concerns. And we're really excited for the JWST high redshift teams to really test those at the limits of redshift 4 and higher. For those who are not used to these systematics, I love this plot. So there really is 2 populations here. Trust me. So if you take the residuals from your Hubble diagram, it should be Gaussian noise should be dominating this of some sort, and it should be centered around 0. But if you plot it against host galaxy mass, kind of the weirdest parameter to say, but it's where it's the most obvious. You see that if you split it at 10 to the 10, this half, which has a histogram here in the dashed line, is different than the high massed half, which has a histogram here in the dark. So the mean shifts by 0.06 mags. You need about 100 or several hundred objects to be able to actually confidently say that that is a not statistical noise. But once you get that, you can start to see that these 2 populations appear to be a little different. Now this isn't on the order of dark energy. The dark energy measurement was about 0.2. but it is important when we're talking about millimag precision distances. And if we correct for mass, stellar mass, but it's actually, say, metallicity, what does that do? What's the bias from that? So these are the concerns that keep us 1A cosmologists up at night. On top of that, Rebecca did an excellent work in 2018 looking at a ton of different systematics and sort of ranking them. And so you can see the systematics that have the largest effect of our dark energy figure of merit is not the stuff that I've just been talking about, all those astrophysics stuff, the science-driven stuff. It's actually the hardware, the linearity of the detectors, the 0 points of the main filters we use. And so the calibration working group that was brought up is incredibly important to us. To bring this up in a different way, David Jones in 2019 released a cosmological analysis, and here was his error budget. You can see the calibration was split up into one, the empirical model that we use for standardization, and then the photometric systems that we use for the main instruments. And adding that all up, it's about 30% of our total error budget for this survey, and will be fairly significant for Roman as well. I'm not going to go into how we do our empirical model because that really would put you all to sleep. So let's think about the absolute flux calibration instead. We are at Space Telescope where CalSpec is from. And so what CalSpec does is it uses Hubble. Hubble is excellent calibration, and it looks at white dwarfs that are mostly perfect black bodies, and they model them. And so you know what you should observe from the models, you go observe it, and that difference is your calibration. But the problem is we don't have perfect knowledge of the source. It is a model. We have good knowledge, but it did actually change 5 years ago. It was small enough that it was somewhat effective. You could see it, but doesn't change the results of previous supernova cosmology. But it is large enough that you would be really concerned for Roman. So what happens if we measure a star in a lab and then throw it into space? If we could just have NIST put a star in space that we know. Well, they're actually working on it. This is called CANDLE. Susanna Doestra is the PI on this. And so what they're trying to do is they're trying to build, this is one of several missions that are working on this in several different ways. They're trying to build an SI traceable artificial star so that you can calibrate telescopes. And so they are working on the design and testing engineering unit that should be ready sort of next year or so. And so the idea is that you have different ways of connecting to the SI system, either by lasers that they did measure in the lab before they put it up in space, or reflecting off the sun, which is another thing that NIST has calibrated extremely well. So I'm looking forward to this to help us with our absolute flux calibration. So we've all said that Roman's going to be awesome. It's going to be awesome just in general for astrophysics. It's going to be awesome for transients, more specifically, and for 1A cosmology, especially. So just to summarize, we're going to get a whole lot more, orders of magnitude more 1As at redshifts that we have not, that we were going from dozen to 10,000. Yeah. And so this will help us understand supernova evolution, help us understand if there are systematics in those H-naught measurements. It gives us a bigger lever arm for the equation of state and excellent constraints on that. Some of those big problems that questions we're having today. And also with one survey, we decreased sort of the systematics in calibration. And we've reduced the number of selection functions and Blomquist biases that we need to correct for and things like that. So in summary, Roman cosmology enters the world at a time when Landis CDM has a lot of questions. It's an interesting time. It's great to see this stage 4 mission coming along. We're going to have an unprecedented number of objects with most of them in a regime that we've never been able to study with 1A cosmology before. But that leads us with new questions, new uncertainties, and a whole lot of work for both the infrastructure and the scientists. I'll take any questions now.
We do. Thank you for the excellent talk. As you already said, slitless spectroscopy is really easy. What is the sweet spot, the optimized technical case in Astro for this?
Like, where do we expect to use it the most?
Bruce, if you want to unmute, you can clarify, but you can also answer the question any way you want.
I have the mic.
How do we think about this as a useful thing? What is its unique abilities for things other than just supernova cosmology?
Yeah, so I think it's multiplexing is its real benefit. And so talking about that spectral time series. And so you will cover about the deep area in prism spectroscopy. And so you're getting something like 30,000 core collapse supernovae. Say about 10% of those 3,000 are imaged with the spectral time series, and you want the top 10% signal to noise, and you can build spectral time series templates from, what was that, 300? Did I do my math right? So I think I think there is a small subset where we get excellent templates of all of these different types of transients that we haven't had before. That'll be mostly, as high signal to noise will be mostly rest frame near infrared, which is new. But we will also be able to use it for typing as you go to lower signal to noise. I think it's the time series information, and I'm just not 100% sure how we will use that, just because we haven't been using it very often. But I think that there's still a lot of information there, and we just have to rethink a little bit about how to use it.
Thank you very much.
Questions?
Yeah, I had a question about the time series spectroscopy that you mentioned. Do you know if there's currently any plans for like how the follow-up would be triggered for transients discovered by Roman, or is that still?
That's the next talk.
Oh, okay. I also saw in your plot you had ones that were at like 2.1 days, like within a few days of explosion.
No, that was max.
Oh, sorry, that was within max. Okay. All right, I don't remember the plot.
We can get close to explosion, but you're to get anything that's actually useful, it's got to be really nearby, or else it'll be really faint.
Do you know if there's any plan to like prioritize flow spectroscopy with Roman for certain subsamples, or still a little too early?
So for the main survey, the spectroscopy is just rolling. It's not targeted in any way, because you want that multiplexing. You're not going to just follow up one object. You're going to follow up whatever's in the field. As you saw, that was one field of view producing that many transients. You're going to always have something that's bright that you want spectroscopy of.
What's driving the 5-day cadence for the prism spectroscopy? Because I don't see any evolution in the spectra. So why is the spectroscopy cadence?
Why? So there's an option. There was an idea floated around that you would do twice the exposure time and 10-day cadence. But I wasn't on the survey definition team, and I don't know why they chose this versus those other options. Brad, do you remember?
Yeah, there is some evolution. Obviously, it's not, evident in the redshift 0.6 ones on there. What with a bunch of lower signal to noise, if you can trace it over time, you do benefit from having some temporal cadence to it. You pay a price in terms of additional slew time versus what Ben was saying. But what we found was that having the extra epochs had some benefit.
You get the age.
You don't know it's a 1A, so it helps having multiple spectra. That's critical for classification.
But also for nearby brighter non-1A transients, you'd want better cadence rates.
What is the spectral range here? This is what you're seeing below.
Yeah, so it's 0.8 to, no, I think it's 0.75 to 1.7 range, and about an R of 100. It's a variable dispersion. You get a higher resolution in the blue, but that one I do know.
This one, yep.
Yeah, so about the previous question you asked about the UV, I think some previous study shows that there seem to be, UV 1A seem to be more diverse.
Yes.
And there seem to be some evolution with metallicity, so maybe with a redshift. So in the worst scenario, they may not be calibratable to high Z. So in that case, if we cannot use the high Z blue band data, how will that impact your the supernova cosmology we can do with Roman?
Well, this is still SALT 3. So this is the models that we've been using in our calibration, in our supernova cosmology. So we're not going all the way into like Swift band UV in this analysis. And so even in the deep tier, you're still able to get a couple bands that are in the rest frame, so the B and V band. And so you should still be able to do the cosmological measurements in that.
Well, what we know is that the supernovae are better standard candles in the rest frame infrared. So by going to, even for the low redshift ones, that's going to be a big advantage for you.
Yes, and with the redshift range that we're really looking at, it'll be really interesting because our rest frame coverage will be dramatically different across our sample. Our low redshift part of our sample will be that rest frame near IR, but our redshift 2 objects will be much more in the blue bands and maybe even a little bit into the UV, rest frame UV. And so those are questions that we need to do, is look at how the standardization varies as a function of rest frame observations. That now gets into some of the science that we need to work on.
Let's thank our speaker again.
Where would that be? Okay.
With that, I'd like to introduce our next speaker, Ashish Malal, I hope I said that correctly, at Caltech University. He's going to be talking about rapid insights, real-time transient classification for Roman. Thank you very much.
Good morning. My name is Ashish Mahabir, and what I'll be talking about, as Rebecca said, is rapid insights, but also going into classification in general, which brings to stride that was mentioned a couple of times before. So this is the broad outline. I'll talk about Roman rapid quickly, but then get more into the classification needs, and especially the inputs that we may need from the community, because Roman is going to be in an uncharted area, and that's where we really need to be able to focus on the kinds of training samples that we get from that. And then availability of data, methodology, resources, some of it related to AI was mentioned yesterday by Fed, for instance, and the ongoing efforts for that. So Julie gave a great introduction about what Roman is, what the depth we're going to reach. So I'll just like to emphasize again that the resolution is exquisite, 0.11 arcsecond. We'll go up to 26th magnitude, and we'll cover about 2,000 square degrees or so, which is not all sky, but still large enough for that kind of resolution, that kind of depth. And the types of objects that we are going to see is everything, not just supernovae. And I, who like to look at all kinds of objects in an agnostic way, felt that there was a lot of supernova-centric things in this conference, which is understandable because cosmology is one of the main things and we should be focusing on that. But one point that I would like to take you from my talk is that in order to be able to make sure that we can identify as many supernovae as we can so that we don't get many false positives and be able to do it well, we need to have samples from other types that are in our training samples. So for instance, in this chart, which is from Gaia, you can see that the supernova are way here in a small area, right? And so there are lots of things. This is from static science, not real-time online science, but again, those are the things that we need to understand, if only to eliminate them to look for supernovae, right? So that's one of the things that I would like to emphasize. So with RAPID, what we are doing is that we'll be doing image tiling, image differencing, rapid detection and classification. Again, Julie mentioned earlier that the charge of getting up to the L2 processing is 48 hours or less. At that point, we will get the data in RAPID, and our charge is within 1 hour be able to characterize and as far as possible simple classification from that. So ZTF, for instance, has several brokers that are, the LSST Roman brokers are using ZTF data right now, and they're doing more exquisite classification. So we'll be doing at least some characterization and quick classification, but we'd like to do more. And again, in order to do that, what would be very useful is to be able to have all kinds of other samples in there. There's a poster in this conference by Skylar, so I encourage you to take a look at that. That has many more details about what RAPID is doing. Including the kinds of data sets that we currently have. So one of the main things that we do want inputs on are these alerts. What should be the alert schema? We are currently using ZTF and LSST related schema, but more inputs from you will really be useful there to make sure that we can provide everything that the community wants. So again, inputs there are really required. So the data methodology and resources. We'll like to do detailed classification and subclassification, and not just from single images, but also from coads. So again, after L2 processing, what we'll be getting is single images, and RAPID is signed up to do classifications from those. But as the survey progresses, there'll be co-added images, and we'd like to do more from that also. And for that, the models will be somewhat different. We'll need to do retrainings and all that, so that should also be going in. And we'll be using existing data and modern machine learning methods. So there are many near-infrared and infrared surveys that have come from the past, and we need to be able to assimilate that data. Again, the community's help in that will be really useful because they cover different parts of the parameter space that we have. And in looking at parameter space, there are a large number of different parameters that we have been talking about, going from, say, TESS with large pixels, but excellent cadence, to Roman, which has a really good resolution, etc. And so there, for instance, with, again, the kind of classification machine learning techniques that we'll be using will be everything, because if you have got time series, then you can get features from that. And for the features, something like random forest, XGBoost is excellent. So we'll make sure that we take advantage of that. But there are modern techniques like foundation models for time series. We'll be making use of that. Some of those were mentioned by Fer in the talk yesterday. But again, there are newer vision transformers coming in, so there'll be opportunities to make use of direct images as well, again, taking advantage of the depth that we have. And some of the things that we may have to do is transfer learning, because if our training is from, say, brighter surveys or with bigger pixels, then we still will be able to learn a little bit and try to take it to Roman. But again, that may not be sufficient. And that's one of the points that I'm going to make. And that's the thing that we'd like to do more before Roman launches, rather than wait after Roman launches and only do it on real data, so as much as possible on that. So several years ago, with a few people, George Orkowski and I published this paper on surveys, which goes into details of all the parameters. So if you're looking at only time domain, how the different delta T baselines are important. So sometimes it's important not to have exactly the same cadence, because then you have a variety of delta T's, which allows you to get different power in your time spectrum. And then the total duration that you cover, the number of exposures you have, or angular resolution, surface brightness, etc., all kinds of astrometric properties, as well as spectrophotometric domain. And depending on which of these to highlight, so TScI has been used a lot these days. It takes a large dimensionality and puts it into 2 dimensions. It shows you something, but it's not really the best representation. Similarly, typically a survey has all these parameters, and putting it on 2 dimensions is generally not enough. So you can highlight any of those by taking them in pairs and being able to show how your survey is greatest in something. But again, there are many nuances, so we need to bring together all these different surveys. And even at the time, just within infrared, there were several, and more studies have been done on many of them in the last several years. And again, all the samples that have been put together, we should be bringing them on. So looking at what we currently have in terms of simulations, so Open Universe 2024 is one of the Roman simulation that exists. There are a few others too. We need to bring those together as well. So in this particular one, there are many different kinds of explosive events that are there. So supernova 1A, supernova 1AX, supernova 2, and so on, TDs, kilonovae, and so on. But what is missing in it right now is other kinds of objects. Kishla mentioned yesterday how there are going to be novae, red novae, other kinds of, there will be a lot of flaring stars that will come in. So objects that are below detection level of even Roman, but during Roman they pop up a little bit and seem like something else. We need to be able to quickly understand them so we don't waste time on them thinking it's a supernova 1A at redshift, whatever, and spend a lot of resources on that, right? And so again, what we'll need is simulating these other types, combine the other simulations that exist, bring those in together. Otherwise, what's going to happen is that we will be able to classify these, but that won't be sufficient. So just from these simulations, we have already done some classification, and that's working reasonably well already. So this is 96.1 and 98.9 using only a few images. This is just for supernova 1A versus supernova 2 from this previous set. And we can already do this A versus B classification quite easily. But to this cat versus dog classifier, if a human being is shown, or if a cow or a camel is shown, right, that's not going to be good at that. So that's something that we need to get into. So for instance, to use this analogy of proverbial humans looking at an elephant when they're blindfolded. So what is this classifier say something else, right? Meaning if someone goes and feels this trunk or these ears, they may think this is an elephant, but it's not. So this is an image that I created using the generative AI, but this is something that others are trying to do in the real world as well. So there is Colossal Biosciences just last week. So they have been thinking of bringing back animals from extinction. So just last week, they were able to create this woolly mouse. It's a real mouse. This is not a generated image, right? So they were able to inject genes from woolly mammoth, where they got it from, and make sure that they get this woolliness. And don't believe what Saturday Night Live said, that the next step is to mate this mouse with an elephant. What the next step that they're going to do is actually be able to put that gene into elephants and try to get woolly mammoth-like thing, which they want to introduce in the Arctic. But that would be what Saturday Night Live said, would be like transfer learning without good setup. Whereas what we want to do is that we want to be adaptive in that. So this is the kind of classification that one can do. One can do hierarchical classifications. And so besides the explosive events, we want to get to all the other kinds. And so what we have been doing in ZTA, for instance, have large number of binary classifiers. And the binary classifiers are where A versus everything else, B versus everything else, rather than A versus B and then get stumped if you get something like C. So there what we are doing, this is an example where an RR Lyrae was shown to the classifiers. And what we have, this series of classifiers, is that the first one is variable, not variable. It says confidently it's a variable. Periodic, non-periodic, it says it's periodic. And these irregular versus various eclipsing ones, they say, no, this is not eclipsing. And then it's not flaring. When it comes to pulsating, it says, yes, it is a pulsating object. Not a delta Scuti or Cepheid, yes, an RR Lyrae. So by giving these different classifiers, we can take a holistic approach. Again, we don't have to have a specific threshold that's a 0.5 and say that, okay, if it's above 0.5, it's of this kind. And so by providing all these different classifiers, we can let the user decide what this object is likely to be. And that, again, what that means is that we do need different sets of samples for all of these things quite well. And so STRIDE was mentioned before. This is a forum where we try to bring together people from different areas, be able to collaborate. So if you have any simulations, if you have any data samples, please bring them together. We meet once every month on Fridays. And these are some of the links which you can use to join. And again, various time domain things is what we are going to be after on all these things right now. One last thing that I'd like to mention is that we can also be, so other things that we are doing in STRIDE, And in RAPID together are various things like star galaxy classification. We'd like to improve that further. So that is going on again with a better set of samples that's going to happen. And Jacob, who's in the audience here, he has been looking at image subtraction using Zogi and SFFT, but we are also trying some of the other methods. So one of the methods is direct subtraction using machine learning. There we have to be careful because we don't want to introduce fictional transients in there. That's why we are taking baby steps in that. We right now can find within 2 pixels 98% of the objects, only the ones near the edges are not being found. But there is a caveat there that if this is when we know that there is one transient and exactly one transient in our image. If there are 0 transients or if there are more than one transients, that's the part that we are trying to work on. So you should be able to hear more about this in the next few months, hopefully. And then I would like to leave with something related to citizen science that we could be doing. With ZTF, we have ZARP, where it's not a citizen science thing, but just an outreach thing. You are able to find transients on your phone using this. For the Android version, it's working well. With iPhone, it's still a little bit buggy, but it should also be coming to the desktop soon. So there what we do is that we introduce ambiguous sources. So we can use neural networks from humans to give us feedback to improve our own networks. And with that, what I'm going to do is leave with this summary. RAPID is moving along with existing sets, but we do need your help to bring together various RAPID, Roman, and time domain related things in that, mainly to make sure that we don't get false positives, because that is something that we will keep getting if we are not well prepared. And many modern ML algorithms are what we are going to be using. So Julie mentioned that October 31st is when the tentative date is next year. That reminded me of a science fiction novel by none other than the astronomer Fred Hoyle. It's called October the 1st is Too Late. We don't want to wait until October 1st to get all our samples in. Thank you.
Just popped up. Have you considered using any 2D image extraction pre-processing, such as 2D CWT, continuous wavelet transform, for example?
Yes, all those are under consideration. Nothing has been eliminated. Nothing has been finalized. But yes, meaning we are considering both 1D as well as 2D features. And so again, what the machine learning algorithms are very good at also is being able to take the images, blow them into million-dimensional spaces, and then decide what is it that they want. So it becomes very black boxy. But some of the things that we are making sure is that we bring in interpretability and explainability, so we understand exactly what features are being used, so that we can make better models out of that as we go ahead.
Thanks for the wonderful talk. So one thing you didn't mention is kind of using spectra, which, you know, we use.
Yeah.
And as Ben mentioned, there will be spectra which have their own limitations, but that's also great data. So will that be folded in?
So that is not part of RAPID as such right now, but it is part of STRIDE. So yes, we'll be looking at it, and there are methods that we can use to look at spectra. So Ben, we should talk more later on, and so that's going to happen. Yes, absolutely. And again, if you have ideas, please bring them on too.
So you classify the transients based on the light curves, but we've seen now that CSM interaction is playing an important role in all kinds of supernovae.
Mm-hmm.
And your transient data set is probably not, or your training data set is probably not having lots of objects with CSM interaction. Could you comment on how you want to tackle that?
Yeah, so again, what we'll definitely need, simulation would be our friend until we get many such things. And if there are simulated things that we can put in the current data sets that we have, then yes, we will be able to use that, because we can combine not just light curves, but images. So there are these CLIP algorithms and their friends, which can use multimodal data as inputs. So we can use whatever combination of data that we have, be able to do that. Again, the main thing would be having a large enough sample to be able to go after that. So that will increase our confidence in whatever we are doing.
Let's thank our speaker. Okay, next up we have Anna Miller from Northwestern University, who's going to be talking to us about leveraging ground-based surveys to maximize transit science with Roman. Thank you very much.
All right, good morning, everyone.
I have to start today with a confession. I really wanted to come and talk to all of you about data. One sentence in my abstract about an ancient civilization, and here we are. You got to think about that joke a little bit. You can come back to it later, that's fine. I want to start with a hypothetical, okay? Imaginary scenario, one that if you haven't encountered, I promise you will over the next decade at some point. Imagine some enthusiastic, highly talented graduate student bounds into your office one morning and they say, I really, really, really want to do machine learning research with you. Now, your first response might be, uh-oh. Okay. And then you think about it a little bit more and you realize, oh, okay, I have data and I know some things about this data and it would be useful to use this data in order to make predictions about the universe. So like any good graduate student mentor, what you do is you decide, okay, yes, together, you and I, we are going to murder about a half-dozen penguins and build a machine learning model that can explain the data that we have. Okay? Now, after a few months, or if you're unlucky, a few years, your model's ready to go and you say, okay, great, let's go make some predictions about the universe. And the universe says, you have a model? You think you have a model? You have a model for me? This is not the universe. This is the universe, okay? And this is actually astronomy. This is transients from space. We spend a lot of time building telescopes, studying things that explode with ground-based telescopes. We understand them really, really well. Now we decide we're going to build some satellite, launch it above the atmosphere, and try to study these things at a waveband that we've never had access to before. All right. We're looking at things that we haven't seen. In machine learning, we refer to this as out-of-distribution samples. And this is something that machine learning cannot handle. It does not do a good job with out-of-distribution. If you haven't trained it to look at the thing that it's looking at, it's not going to do a good job of telling you what you're looking at. Okay, so I'm going to talk about a few lessons for things like Roman today. This is one of them. To make this very, very concrete, in my group, we've been pushing very hard on building machine learning models to identify very young transients in very nearby galaxies. Here's a beautiful discovery we made a couple months ago. This galaxy is at 20 megaparsecs, very bright supernova. We found it before anybody else. But look really close. Look really close at that new image. It's a little hard to see, but there's a couple streaks that are moving through it, very, very faint. Our machine learning model had no idea that there are humans that their favorite thing to do is to launch small constellations of satellites into outer space. Okay? The model didn't know. The model had no means of saying, actually, I don't think this is a real explosion. This is something else. Okay? Okay, so I am talking about how we can use small telescopes, ground-based telescopes, to support the science that's going to be done with Roman today. By analogy, I'm actually going to start with a different project. I want all of you to imagine Rubin. Right? I contend that not all transients are created equal. In fact, the ones that are very, very, very nearby, for which we can get panchromatic observations, are the ones from which we can learn the most physics. We've heard a lot about that this week. So let's see what a type 1a supernova at a redshift of 0.1 will look like to the Rubin telescope. And I'm going to be talking about this in the context of a new project that I'm working on called the Lucia-Schmidt Southern Survey, which is a wide field time domain survey that we're starting very soon in the Southern Hemisphere. Okay? So here's a type 1a supernova at redshift of 0.01 as it would be observed by Rubin. Incredible, deep upper limits, constraining, who knows, because there's a long gap in between observations. Wonderful observations while the supernova is bright that saturate your detector, and you can actually learn a whole lot of what's going on. Okay? LS4 is going to fill in these gaps. And by analogy, you could imagine a similar thing happening with Roman by observing every single night, creating a beautiful light curve in which you understand quite well both the time at which this thing exploded and if there is anything unusual going on in the light curve, what's happening there. Okay? But what Rubin buys you that hasn't ever happened in a large systematic way before is everything after the supernova has faded below the detection limits for your small telescopes, right? So in the next year, Rubin and Roman come back to this field, and you get this beautiful decay light curve, right? A year after explosion, 2 years after explosion. We don't have a great model for what type 1a supernovae look like years after explosion in the infrared, but you can imagine Roman just continuing that light curve well beyond the bottom of this screen here. So one of the ways that we can support these missions is by filling in the gaps in the observations that they have, and also by discovering very bright things so that we can understand what's happening at late times. And you're going to hear later today from Orr, who will tell you a lot about the physics of what you learn by getting these late time observations of supernovae. I'm going to take a quick aside to tell you a little bit more about LS4. So I'm the director of this new project. We're doing this on the cheap, and the way that we can pull this off is by reusing everything. So the ESO Schmidt telescope has been unused for about almost a decade now. We're going to be using this telescope with a camera that already exists, but we're going to fully fill out the focal plane so that we can get 20 square degree images. The detectors are leftover detectors from the dark energy camera. So basically, these were kind of just sitting on a shelf over at Fermilab, not doing anything for a very long time. And so we're throwing them on this existing camera into an existing telescope in order to do this new survey, which will run concurrently with Rubin. We have a 268 megapixel camera with 1 arcsecond pixels, and we'll go down to about 21st magnitude in the G band and 20th magnitude in Z. We do not have room within our telescope tube for a filter exchanger. So instead, we're using a slightly novel strategy of putting 4 different filters that are permanently affixed in front of the focal plane. And we're going to leverage the fact that our detectors are very sensitive in the red. So half of our focal plane is going to be getting I-band photons, and then the 2 other quadrants will be covered by G-band and Z-band. So we're going to dither across the sky in order to get colors, and we're going to be especially red sensitive. This, again, is somewhat well matched to Roman. 90% of the observations that are collected with LS4 are going to be available for the public. So all of you are LS4 scientists, whether you know it or not. And this is primarily going to be focused on extragalactic fields, looking for transients of different types. We will also have a campaign that happens in the galactic plane, where our primary motivations are to go after microlensing events and short period eclipsing binaries. We will be producing alerts of the transients that we find, and they'll be blasted out to the public in real time, same time scale at which we get them internally. OK, so I started with data. I shifted to how we can use small telescopes to support our Roman. And now I want to talk a little bit more about machine learning. Here is a task that I think many in this room have had to deal with, which is looking at difference images and deciding whether or not you have found something real. This is a task that all of you are sick of. Whether you are some professor that's been doing this for many decades, or if you are a first-year grad student that's only been doing this for 1 month, you don't want to do this anymore. And we decided in ZTF we don't want to do this anymore. And so I started working with a graduate student at Northwestern, Nabil Rahimtullah, to see if we could create a model that would make it so that we don't have to do this anymore. And so that's where we conceived the idea for BTS bot. So this is a machine learning model. It takes multimodal inputs. We have images that come from ZTF, as well as a little bit of information from the light curves. And what we want to do is understand, can we automatically identify all of the bright transients in ZTF? And we compiled it. There were thousands of person hours that went into this task in the first few years of the survey. And we've now offloaded this to the machines. In short, yes, we can do this. You heard about it briefly yesterday in Fed's talk. But just to highlight very quickly, supernova 2023 TYK was identified by this BTS bot system, which then requested a spectrum. A spectrum was taken, a separate machine learning model that we developed called SN1A score, classified the spectrum, and then BTS bot wrote a notice to the transient name server so that we had a fully automated discovery of a supernova. OK. You should say, OK, yeah, like cool little party trick, but why does this actually matter? And indeed, this particular supernova is a 1A at a redshift of 0.05. And aside from the fact that we happen to do this automatically, no one would ever care or know what this supernova was, again, for the rest of your lives. Okay? But I'm going to quiz you on the number of supernovae you know at a redshift of 0.05 by name when we get to the break. OK, so moving on, right? What does this buy us? This buys us automation, and automation buys you speed. So the way in which we've been able to push this recently is by looking for, as I said, very young supernovae in nearby galaxies. And we had a pretty, I would say, remarkable discovery at the end of last year, supernova 2024 JLF. And what was so remarkable here is that the robot found this thing as soon as the data was processed and requested spectroscopic follow-up, which we obtained 7 minutes later. And we've spent a lot of time this week hearing about how important it is to get observations right after something explodes, okay? And it is unreasonable for us to ask humans to constantly be looking at a stream, right? I like to read a book to my kid before he goes to bed at night. I don't want to have to not do that so that I can see if something new has come from ZTF. But when we automate these things, we can do this very quickly. And so if you want to do things like flash spectroscopy, introducing as much automation as possible, as much speed as possible, is very, very important to execute that particular science. Okay. We are also building this out. So we now have a program to do priority 0 triggers with Swift. So we're not just getting spectra very quickly, but we are also getting UV photometry from space. Okay, yeah, see, I've worked in space a little bit here with Swift in order to get very early UV observations, again, which we've been told about is very, very important. Okay, so in conclusion, all right, I want to state that nature, or humans, always find a way to deliver out of distribution sources. So if you want to build machine learning models, I highly encourage all of you to do this on small ground-based facilities where this can be done with low cost and low risk. If you have a model that doesn't work well on something with a 1, price tag, you probably shouldn't be trying to use it on something with a 3, price tag. All right. I also have demonstrated that small aperture facilities, and in some cases, when we're talking about Roman, even larger aperture facilities, can fill in gaps as we get these very deep time domain surveys. And this can enable a lot of science that hasn't been possible at the scale at which we can do this with things like Rubin and Roman in the next several years. And then we heard very briefly from Ashish about transfer learning and how this can be really useful, right? Have some model, make it work on something like ZTF, and then figure out how you can apply this to Roman. I think LS4 is the place for all of us to learn how to do transfer learning, okay? There's lots of ZTF data that's out there, many people that have built good models with ZTF. LS4 will be similar, but it will be different, and this is a real opportunity for all of you to figure out how you're eventually going to be porting the work you do to larger and more complex facilities like Roman. And with that, I will happily take any questions. Thank you.
To the audience.
Nice talk, and obviously this is a huge result. But my question is, maybe I missed something, but how often does this bot trigger something that ends up not being anything positive?
So the question is, how often do we identify false positives and trigger on them with our automated robotic system? And the BTS bot has a false positive rate that is a few percent. I have to look at the paper, remember the exact number. It's less than 10%. It's I think even a little bit less than 5%. When it comes to triggering spectroscopic resources, I will admit there were some growing pains when we first turned it on. So we did have a few spectra that didn't turn out to be actual supernovae. But now that we are sort of fully up and running and we've worked out some of those initial kinks, we are operating at false positive rate that's 5%. Yeah.
This was done on ZTF data.
This is all done with ZTF data, correct.
Yeah, Adam, thanks for the talk. Can you talk a little bit more about how you're going to serve data to the public with LS4? Will it be light curves? Will it be force photometry services? Will it be images? And kind of like what your archive plans are?
Yeah, so the question is about how data from LS4 is going to go out to the public. So there will be full images that are released and distributed via the ESO archive. The timescales for that are still not perfectly certain because they depend a little bit on latencies that will be associated with us getting the data from Chile up to Lawrence Berkeley Lab, which is where the pipeline is going to run, and then transferring from Lawrence Berkeley Lab into the ESO archive. We're hoping that that's a relatively quick time scale, but it may be that that's a month or two. We're going to be generating alerts, very similar to what's happening with ZTF. And those are going to be going out through various brokers that you've come to know and love in quasi-real time. So essentially, as soon as we've processed and identified transient candidates, they're going to be released to the community. We do not, at the moment, have forced photometry incorporated as part of our pipeline. So if you want to look for an analogy, it'll be more similar to what the alerts looked like in the first 4-ish years of ZTF than what alerts look like from ZTF right now. And we've developed a schema for our alert packets that we've tried to mirror what's going to be delivered by Ruben as closely as possible.
One more question, sir.
Great talk.
Thank you.
Does it have anything that can handle with limited resources, like in the event that you detect 2 transients? Is there any prioritization that occurs?
Sorry, you said does it, and I'm not sure what you're. So does BTS bot
account for prioritization? Like if you were to detect 2 transients and you need to choose which one to follow up on.
Okay. So internally within the system, BTS bot is making requests in the same way that a human would. And then we have a separate system for our main spectrograph, which is the SED machine on the Palomar 60-inch, which has its own internal queue manager. And so for things that we suspect are very, very young and very, very nearby, we request observations at the highest priority possible. So this is how you can get something like a 7-minute turnaround. But if we have identified a supernova that we think, oh, this is just going to be bright enough that we could get a spectrum, then the request goes in at lower priority. So the bot is not making those particular decisions, but it is being intelligent about the way that it is requesting data.
And with that, let's thank our speakers.
Thank you.
And if you have any more questions for our speakers, you can find them during the coffee break, which I believe is.
Coffee breaks now, and I hope everyone's excited to join the Roman community. We'll come back at 11:20. That's 5 minutes behind schedule, and hear about Euclid. All right. Thanks.
For the record, my talk ended with 0 seconds. I did it.